quantity we call strain is. And strain is a feature that's the critical quantity that is used in describing two of the types of geologic structures we'll talk about, which are folds and fabrics. Those are the two features that are critical in that particular context. Folds are a classic example of curved structure, right? So that's heterogeneous deformation, whereas strain is something that's a smaller scale, and I'll talk about some of that today. So what I want to do today is carry on with that concept and try to use what we learned last time, but in particular talk about strain in terms of its geometric features, because there are some peculiar things that are produced that are entirely by strain that are slightly counterintuitive until you start thinking about the consequences of strain. In particular, we'll talk about ranges of distortions that range from the simple box, like we talked about, to shear and some of the things that result in the context of both of those things. And we're going to start with two-dimensional strain, or just a cross-sectional view, and then we'll work our way into 3D. And you can bring a couple of rocks, which are not necessarily the greatest illustration, but what the heck. This is the case we're in the middle of talking. I gave you this example last time. It was a theoretical thing, which was, we talked about that in the context of the quantity strain, where you start with, I tried to draw this on the board, but you can see this better than my crappy drawing, is that if you start with a circle and you have various lines drawn on there in different increments. So you could take, for example, the 45 degree and 45 degree minus 45 degree lines here, track them through the deformation. You can see they change their orientation and they change their length. And that's the generalization of the changes of those four strain parameters. It's really three independent parameters, but the four parameters, which are the two elongations of the line reference lines and the angle change between them. You can think of it that way. I forgot to mention, by the way, last time, technically, the term gamma, the shear strain, is not the real mathematical quantity, but that's irrelevant. You'll never have to deal with it until, you'll probably never have to deal with that relationship. It's just the way the math falls out. You don't want to see the math derivation, trust me. Although there's a link on there if you want to go to Wikipedia that gives the whole derivation. Wikipedia is great sometimes. The main point of this diagram, though, is to illustrate the effects of progressive strain in this particular end member characterization of strain, which is often referred to as pure shear or coaxial strain. It's what you would first think about in terms of distorting something. You push on one end and you pull it in the other direction. So in this case, the forces are involved as a compression in this direction and extension in this direction. So, and those axes stay constant in the sense of the driving forces don't change in this type of deformation. So you simply squash it and extend it out. Hence, it's so-called coaxial strain. Alternatively stated, the stresses and the strain axes are the same, which we'll deal with a little bit later. The important part about this, though, is that as the strain progresses, this is increasing deformation, right? So you start from a circle and you get to a strain ellipse, which gets to a bigger strain ellipse, gets to a bigger strain ellipse. And you can actually quantify that increase, by the way, of the ratio between the long axis and the short axis of the strain ellipse. And that's what we do, actually. We'll talk about that again in just a moment when we go to 3 dimensions. But that ellipticity is what you could actually measure in an object. And in fact, that ellipticity is a ratio of stretches, for whatever it's worth, those two quantities we talked about. So it's the maximum stretch divided by the minimum stretch. The key point of this diagram, though, is to illustrate a counterintuitive thing, even in the simplest type of strain, is that there's an odd effect such that line elements that start off, these are starting at approximately equal, if you take 15, 30, 45, 60, and 70, those are equal angle increments, right? There's an 80 stuck in here as well. As you progress, notice how 15 quickly is, all these elements are moving towards the elongation direction. So if you're a marker caught up in this flow, you rotate towards this direction. And so even the element that starts out at 75 degrees after this much strain is only about, what is that, maybe 20 degrees off of the shortening or the elongation axis, excuse me, or perpendicular. So that basically line elements move away from the shortening direction towards the elongation direction. Now, one way to think about that is that's a simple qualitative illustration of how materials can develop a preferred orientation by strain. Because if you start out with random line elements and you deform them, just the flow will make them flow into parallelism with the elongation direction in this two-dimensional context. And they're not rotating per se in the sense of you're taking them and physically rotating them. They're rotating as totally as a response to the strain or the distortion in the rock, not a rigid body rotation. That's a different component in that particular context. So there's a double, in this case, there's no other rotation going on, yet elements rotate. And they move towards the elongation direction. The other end member that we can often think about in the context of two-dimensional strain is simple shear. Now, it always kind of seems weird, like there's pure shear and simple shear, but why the other one's even called shear. In some respects, it's easier to think of it as coaxial strain and simple shear, but it's also called pure shear, so you just have to remember those stupid terms. But simple shear is nothing more than a card deck, which is the one that we analyzed briefly as a theoretical thing last time, which is if you take this system and you just shear it. So these line elements move exactly parallel to that. You can get a card and deck of cards, draw a circle on it, and you can do this experiment yourself. In fact, I've done that before as a lab experiment, but it's pretty good, whatever. You can do this with Adobe Illustrator too, if you like Adobe Illustrator. It's got a shear tool. You can do your own simple shear experiments. But simple shear is an important distinction because it also generates strain. So the flow, this is just a different type of flow, that it takes an initial circular object, and as strain progresses, you build an ellipse that gets bigger and bigger and bigger. Now, the important part about simple shear is that this is a very clear example of a geologic process, because simple shear is just the flow equivalent of a fault. Because as the material moves in simple shear, you're just moving one piece of rock past another. So if you shear those rocks, you're generating this process. So simple, I always get it, simple shear. It's like, you know, it's like the sheet ice slit or whatever, right? Simple shear is hard to, is an important process. And it's because of that there are a lot of things that are developed relative to it. But there's a very, very peculiar thing that develops in simple shear that sets it apart very distinctly from pure shear coaxial strain. And that is, there's a very big distinction between what you would call the incremental strain axes, which you could think of as the stress or the driving forces, versus the accumulated deformation, which is the strain or the finite strain within the material. And it's illustrated graphically here in a very well. At no strain, of course, you start with a circle, but shown here are a series of reference lines, A, B, C, and D, that are in the initial configuration on this strain ellipse. And again, you could do this yourself with a card deck and show this to be true. If you shear this 30 degrees, you make an ellipse or a strain ellipse, and you could calculate the ratios, the elongations and the like from that theoretical relationship. And the long axis here, in this particular case, sits here at, I guess it must be B, that's about the long axis of the strain ellipse sits right there. So in its undeformed condition, it's back here. Well, I know what A is. A is 45 degrees off this angle. You can show theoretically, very, very easily, not relatively easily, that the incremental strain, you can see here that this is shortening and this is elongating, and that's the progression that goes on in the system. You could also see what that means theoretically is incremental shortening direction is in this direction at 45 degrees off the shear plane, and the incremental elongation direction is 45 degrees the other way, which is line A, or reference line A. After deformation, though, note that after 30 degrees of shear, this line that starts out here ends up here, which is less than 45 degrees. And the new long axis of the strain ellipse is here. I go another increment of strain, and the new long axis of the strain ellipse is at C. If I back off to where I started, C was there. I go over here one more increment. The long axis is here at D. I started back over in here. What's happening is line elements in this particular type of strain are all progressively rotating towards the flow direction. Doesn't matter what direction. The only line that doesn't rotate is a line in this orientation. Any other line progressively just keeps rotating and rotating and rotating until it lines itself up with the flow. Is that surprising? No, not really. You can just think about that qualitatively. If you have something like a fluid that's between two rigid planes and you did that, everything's going to smear, it just smears out towards the direction of flow, right? But it's tremendously important distinction in the characterization of what happens to rocks in a configuration of this versus the other one. Because in this case, there's this continuous rotation, which is a rotation which is shear-induced rotation, as opposed to the pure shear example. Let's go back to that one. In the pure shear example, whoops, backwards. In this pure shear coaxial strain example, all line elements on this side rotate this direction, but it turns out all elements on this side rotate the other direction. So some line elements rotate one way, the others rotate the other way. In simple shear, all line elements rotate in the same sense. That is necessarily important because that can be exploited as an indication of the sense of shear, and it's used routinely in geology to understand how materials flow. And it was the characterization of that was a development maybe 20 years ago that really, really helped our understanding of a lot of field problems and of the generalization of the motion that occurs within complicated rocks that float. You can actually make a graph that characterizes that relationship. This angle, theta prime, is the angle between the long axis of the strain ellipse and the shear plane. So it starts at 45 degrees, and as gamma, remember the tangent of the angle, or the shear angle, gamma, as this increases, so when gamma is 1, psi is 45 degrees. So this is 45 degrees towards the next input. Gamma becomes 2. I can't do that kind of trig in my head. But you see, but already with only a shear factor of 1, or a shear factor of gamma 1, this angle is decreased to about 30-some degrees. And as you keep going, it just keeps going and going and going, such that this goes asymptotic to the lower boundary. So that under large amounts of shear, theta rotates toward, or theta prime, whatever we're going to call it. The long axis of the strain ellipse rotates towards the flow direction. What that means in practical terms, back to this, is, or not just graphically, that's just showing this relationship. As the strain accumulates, the finite strain, which is what's represented by the strain ellipse, rotates towards the flow direction. But the incremental strain axes stay the same. And that's what's important in this whole system. They always stay there, and everything else rotates within that reference frame. And it can be quantified very simply by that general relationship. Now, there's some other peculiar things that occur in here as well. This is just the accumulation of ellipticity. So on this axis, is the ratio, the long versus short axis of the strain ellipse. So you see that already by the time you get to about 1.6 or 1.7 something over in here, where the shear strain is only 1.7, the ellipticity on the strain ellipse is already up to like 4 to 1, so 4 times as wide as much as it is wide. Think about that in terms of a geologic process, right? That means that if you have a 1 meter thick shear zone, or a zone of shear that starts out a meter thick, already by the time that thing has moved only 1.5 meters, you've already accumulated that much strain by this process. So strain accumulates quite rapidly in that contact. It's becoming quite prominent as an ellipticity. And so that's one of the reasons why rocks behave the way they do. There's another thing in here that's sort of even more counterintuitive that has to do with what happens to various line elements that are caught up in this flow. And it's easily illustrated by just taking a card deck and superimposing a triangle on it, where if for line AC is parallel to the flow, right? So nothing happens to it, right? Makes sense? It's just a card deck, right? It starts with a card, it stays a card in the theoretical thing, but it's the same in the flow, right? It won't change. But other line elements get caught up, and they're going to have a different history depending on their initial orientation. So let's take AB, for example, as the simplest one to start with. Line element AB is going to shear in this direction. Line element AB goes in this direction. So what does that mean? It just stretches and stretches and stretches. It always gets longer and longer and longer in the flow. And it'll go asymptotic. It'll get smeared out into the flow as well, just like the strain ellipse. But since it's a marker, it starts out here, but it always stretches. So it's strain on this marker that's shown over here is AB. Where's AB? I'm on the wrong one. This always is positive. Remember, positive E is elongation. So that line always elongates. But take this other one. This is what's counterintuitive. CB. CB, as this shear, is going to first rotate towards being perpendicular to the shear direction, which is the shortest it'll ever get. But that means initially it gets shorter as it shears, but then as it goes beyond, then it starts to stretch, which is the really weird counterintuitive thing, so that its strain is such that that line element first shortens and then stretches. When people first recognized this, it was a lot of people, I'm sure, sat around and said, oh, I've seen that, right? What might be a manifestation of that, the one I've seen many, many times, is you have rocks that are folded. They first get folded, and all of a sudden they're boudinaged, which is totally bizarre, right? Why would something fold and then boudinage? Makes absolutely no sense. That would be a complicated kinematic history. Shortening and then stretching, like an accordion. In this particular case, you can, in some cases, you could explain it entirely as a result of the strain. Flow. Just laminar flow in shear can produce exactly the same effect. And so local things can be confusing without thinking in the context of the flow that gives rise to the system or the strain within that problem. So go back to reiterate that a little bit. Just